Hello all, I'm Dean Johnson, The Rock, the highest paying actor of Hollywood, and welcome back to my video. Anyway, so in this lecture we are going to learn about leaderless replication. Okay, so till now we have seen what is single leader replication, what is multi-leader replication. Now we are jumping to leaderless replication. So what is basic theory of leaderless replication is that there is no leader. Obviously, we can understand by the name. And whenever a client reads or writes, okay, he writes or reads to any of the DB, okay, any one of the DB, cool. But and then in future they sync with each other, okay, and like the data is uh, all over the like whatever this cluster, okay. Now you can say, won't we get lots of write conflicts? Obviously, we'll get lots of write conflicts if this was the structure, correct? So how basically how actually the leaderless replication works? Let's see. So actually what happens in leaderless replication, the client, okay, he writes to multiple DBs, not one DB, okay, and the client who is receiving, so client who is writing, he also writes to multiple DB, and client who is receiving, he is also reading from multiple DB. Okay. Now, what happens is that when you are reading from multiple DB, you get the most updated data. So you find all the DB. So for example, okay, let me make one more picture. So what basically happens is something like this. Okay, so let's say previously A was equals to 0 in all the DBs. Okay, this is like DB1, DB2, DB3. Okay, whatever. Now what happened that I updated A equals to 1. Okay, so when I updated A equals to 1, I updated it in this 2 DB. Okay, so let's say the epoch number, the snapshot versioning number basically is E1 now. So previously it was E0, now it is E1. So in this two, we got updated data, which is A equals to 1. Okay, so A equals to 1, whose epoch is 1. Okay, and now there is a reader. Okay, reader comes and reads the data. Okay, when he reads the data, what he finds out, let's say he reads from this one, DB3 and DB2. Okay, one place he finds A equals to 0, whose epoch is E0. One place he finds out A equals to 1, whose epoch is E1. Okay, so obviously E1 is bigger than E0, so he will get the best data, which is A equals to 1. Okay, so basically this is how the leaderless replication works. Okay, so after that, what else modification can we do? So what we can do is that once it finds out that this client finds out, okay, that this guy was little bit outdated, what he can do, he can say this guy, hey buddy, you are not updated. A equals to 1 is the new updated value whose epoch is 1. So this guy will also update from A equals to 0 to A equals to 1. Okay, and he will also update to E equals to 1. Okay, cool. So when we say that the client also sees the DB that you are outdated, okay, we call it as read repair. Okay, we call it as read repair. So can we say that if read repair is there, then the whole DB is strongly consistent? Uh, Most of the cases, but not always. When is this not applicable? Let's see. So let's take this case, okay, in which initially in all the DBs A was equals to 0. Okay, A was equals to 0. Then what happens that this client writes a data that A equals to 1 in all these 3 DBs. Okay. But when this guy reads, he reads from this 2 DB where A is still equals to 0. So he gets the stale data, correct? So what can be the solution? So the solution can be, if this guy reads from 3 dB and this guy also writes from 3 dB in this scenario, I'm just saying, okay, then he will get A equals to 0 whose epoch is 0 in 1, A equals to 0 whose epoch is 0 in 2, but A equals to 1 whose epoch is 1. then he can say that this is the highest one and I will take this one. Okay, so this thing he can say, right? So this what we call is quorum. Okay, but how will the quorum get maintained? If read number of dB from which this guy is reading plus number of dB in which he is writing, okay, is greater than total number of nodes. So how many nodes are there? So there are 5 nodes. So if read, which is equals to 3, this guy, plus write, which is equals to 3, is greater than 5, then this problem will never happen. Then the quorum will always be maintained. Okay. Okay, cool. So can we say now everything is completely consistent? Not exactly. Let's see when. So let's take this example. Let's say there are 3 databases. Okay. So this database is present in India. This database is present in US. This is present in Europe. And initially, all of them was having A equals to 0. Okay. So what happens? The person sitting in India, okay, what he does, he says A equals to 1 to Indian server as well as to the US server. So in Indian server, it reached at, let's say, 1 second. Okay. But in US server, it took like 3 seconds to reach. At the same time, what happened that this US person, okay, what he told A equals to 2 and his A equals to 2 got updated in US server at 1 second. Okay. But in Europe server, it got updated in, let's say, 3 seconds. Okay. And then at the same time, what happened? There is another guy who is sitting in Europe. Okay. He updated A equals to 3 and it got updated in European server in 1 second, but it got updated in Indian server at, let's say, 3 seconds. Okay. Now you can understand the problem, right? As this DB got A equals to 2 and A equals to 1 at the same time, there is a race condition. Similarly, in Indian server also there is a race condition. Similarly, in European server also there is a race condition. Now no DB agrees with each other that what is the actual value of it. Correct. So this is problem number 1. Is this going to happen every time? Like this is extremely rare. Like what you can understand that it should be a coordinated like something coordinated operation to break something like this. But yeah, this can definitely happen. Second problem is Second problem is, let's say there are 3 DBs. This is the writer and he wrote A equals to 1 in all the in this 2 DBs. Okay. But what happened that he was able to write in this DB, but he was unable to write in this DB. Okay. But the reader, he's reading from this DB and this DB. But obviously these 2 DBs have a older value, so he gets a stale read. Okay, so he gets A equals to 0. Obviously, what we can do, like we can apply something like two-phase commits and say that if this guy fails, then roll back the changes. Okay, but obviously that will take some time and rollback can cause some problems like conflicts or something. Okay, so this is the second problem, that it is not 100% consistent. It is eventually consistent. Okay. Now your question can be, do we only completely wait for the like read repair? Is there no replication happening? Obviously there is replication happening. So let's say there are 3 DBs, okay, and this is the client who writes A equals to 1 over here and A equals to 1 over here. After some time, okay, if there is no read repair or anything, they will replicate to each other. Now you may say, like, will they replicate the whole data like what we were doing in version vector? So let's say there is A, comma B, comma C, comma D data. There is also A, comma B, comma C, comma D data, but here there is only B, comma C, comma D. Okay. So will it send the whole A, B, C, D over here, or will it send only A? Well, it will only send A because obviously you can send the whole data, but the data can be extremely huge, right? So that will completely consume your bandwidth. Okay. So what else can you do? You can send only A. But like, how can you understand that you only have to send A? If you just linearly traverse, like if you just linearly traverse it may take ages because the dbs can be like very big. So what we use Merkle tree. Okay, so this is how the Merkle tree is basically made. So let's say A equals to 1, B equals to 2, C equals to 3, D equals to 4. It passes through a hash function, okay, which says that A equals to 1 is like hash 100, B equals to 2 is hash 200, C equals to 3 is hash 400, D equals to 4 is hash 500. So when this two got combined, the total hash function become 300. Okay, basically addition of these two. Let's say 100 plus 200 equals to 300. Similarly, when these two combines, okay, this added up to 900. So 400 plus 500 equals to 900. Okay, and the total is basically 900 plus 300, which is basically 1200. So how the Merkle tree will look, it will look something like this. Like this one will come here, this one will come here, this one will come here, and this thing. Okay, hash of each of the things. Okay, so this is the Merkle tree. But now how can we use this Merkle tree to find out the difference? So before saying that, I will just like to say that, like, when we do linear search, it's O of n, but when we do a tree search, it's log n, right? So yeah, let's see now how can we find out the difference. So let's say there are two dbs. Okay, this is db1, okay, and this is db2, okay, and they have the Merkle tree something like this. So first we go to head. Okay, we see there is a difference, which means there is some data which is not equal. Okay, then we go, let's say, right. Okay, we go right, we see again there is a difference. That means that difference belongs somewhere in the right. Okay, and then we go to left, we see there is no difference, both of them are 900. Okay, so obviously we can basically skip traversal of the whole, this whole part. Again we go to left, we see there is a difference in the value. Over here it is 100, over here it is 50. So this is the place where there is difference. Then we go to right and we see the different, there is no difference. Okay, so we don't traverse. So let's say if this place was a equals to 1 now, and previously it was a equals to 0. Now we found out that only a equals to, the value of a has changed. Okay, so basically this is how the Merkle tree actually works. Cool. Okay, so concluding this video, what we have seen in the leaderless replica is that when there is a leaderless replica, read plus write should be greater than n. Okay, so read plus write should be greater than n. Okay, and if there is some uh, steal data in one of the reads, okay, we do read repair, and if there is no read repair happening, what we can do, that we can see the changes that happened in this db versus this db and replicate only the changes. Okay, also by the way, this replication of changes is called anti-entropy. Okay, anti-entropy, ANTI entropy, ENTROPY, anti-entropy. Okay, cool. So this was all about read replica. So sorry, this was all about leaderless replication. And by this, by here, we are concluding our replication part. Like we have finished our replication part. Next video, I will just make a conclusion video of what is replication. Thank you.